This is a solution video for Temperature Control Lab B for the Advanced Process Control and Optimization labs that we have for the Arduino. If you come to the course website, APMonitor.com/do, and then if you scroll down to Arduino Lab and select that, it'll bring up this web page where it goes through the information about the lab, and I'll share with you some of the data sets, so even if you don't have a lab, you'll be able to follow along with this. Here are the problem statements. This is going to be problem B right there, and we're going to go down and look at this, some of the solutions. Okay, so here's lab B, and I'll post this video there, and then there will be the data files that you can access here. Here's some steady state data that we'll be using, and then also some dynamic data. Okay, so you're going to need both those. We'll just show you how to import those into Python, or you can generate your own. We're going to start with this first script right here where you generate the data. Okay, so I'm going to just get this started. So during the video we'll generate the data, and then we'll have it hopefully by near the end. Okay, we're going to import NumPy and Pandas and also the Temperature Control Lab. You can just pip install that if you don't have it. And then we'll import time as well, matplotlib, and then we'll name our file. We'll give some heater steps, first of all for heater 1. So let me go ahead and just go to the diagram for this one. Here we have two heaters side by side, and here's the Arduino lab. And we're going to step, first of all, this is going to be T1 right here. There's our heater, and there's our temperature sensor. Here's a second heater and the second sensor. Okay, so we're going to put in these steps. So from time step 10 to 200, we're going to have a value of 80. And then from 200 to 280, we're going to be doing 20. 280 to 400, actually 399, it'll do 70. And then from 400 on, it'll do a percentage heater output of 50. And then for heater 2, similar, but we're going to be generating these steps. I'll show you a diagram here of what this generates, and we'll generate it as well for ours. Okay, so we have heater 1, which is in the red, and that steps up to 80, down to 20, up to 70, and then down to 50. And then there you can see heater 2. And what we want to do is try to generate this data, and we're also going to create a model using both first principles, energy balance, as well as deep learning. Okay, we're going to connect to the Arduino. We'll open the file, and then for the range of for 10 minutes, so 601 seconds, 601 time steps there, we're going to set the heater. We'll just display the time in the heater 1, heater 2, and temperature 1 and temperature 2 to the screen. We'll wait for 1 second, and then we're going to write our file with that additional data. I'll make this just a little bit bigger so it doesn't wrap there. Okay, and then we'll close the connection to the Arduino once we're done. Now we're done, we'll have our file, but you can also go ahead and just read the data in with read CSV and then plot the measurements. So at the very end, we'll plot the two heaters, and then we'll give it a legend, and then have this second subplot down here, and put in our temperature 1 and temperature 2, and add a couple things to make it look nice, and then we'll save the figure and show the plot. So what I'm going to do now is just go ahead and start that. Okay, so let's see, I'm going to go ahead and just start this one, and we'll let it run during this description of what we're doing. Okay, so I'll run this, it'll connect to the Arduino, and then start collecting some data. Okay, alright, so there you can see the heater values and the temperatures. Now at a certain point, the heater 1 is going to turn on to 80%. So you can see that right here, 80% for heater 1, heater 2 is still off. So it's just going to go through and march through for 10 minutes these values, and at the very end it'll surprise us with a plot that will pop up. Okay, so let's go on to the next one now. We've got our energy balance. So we want to try to model this with an energy balance, and we're going to use some of these constants. We'll develop this transient energy balance. Okay, and then we'll also have these equations right here. So we'll just have those two energy balance equations. It's just accumulation equals convection, radiation. Okay, here's your convection to the second heater. There's the radiative heat transfer to the second heater, and then there's your heat input to the first heater. Also, we'll have accumulation, convection, radiation, convection to the first temperature sensor and heater, and then also radiative heat transfer to the first one, and then the heat input from our second heater. Okay, so we have these two that are just side by side. So let's develop an energy balance. Okay, we're going to do that with GEKKO, and we'll also import some data that we have just to be able to compare our predictions to what GEKKO produces. Okay, we'll have our 601 points, and then we'll create some times, m.time. So we have GEKKO, there's our model, and then m.time, that's going to be our times where we want to simulate this. We'll have parameters, these are our heater values that we defined previously. But now we need to feed these values into the Q1 parameter that we just had set. Okay, so we're going to feed that into Q1.value for the GEKKO simulation. And we'll do the same thing for Q2. And there are heater values right there. Okay, and then we're going to have, or we can define it this way as well, where we just say Q1 equals m.param. And you can put the value inside there. So you can do either one, like we did here, or you could do it like this. Okay, and then we'll have the initial temperature. And you know, it looked like it was just a little bit colder in here, so I might need to change those to, you know, something like 17. Okay, and okay, so there we go. And then if you want to change this, you can change it to U value of 10 or 20, you know, whatever you want to change it to. So we can go back and change those later. There's our mass, there's our heat capacity, our area, and I'm just going to put everything in SI units so I don't have to do any unit conversions. And there's my alpha 1 that relates percent heater to watts. So at 100% on, I'm saying that we dissipate about 1 watt of heat. And then for the second one, it's a little bit less powerful. That was in the firmware. We changed that, so it'll have a gain about half of what the first one has. Okay, and then we'll have epsilon and sigma for radiative heat transfer. I'm going to define my two variables. These are going to be T1 and T2 that we see there in the energy balance. And then we'll also have our terms, these ones in blue between the two heaters, and we'll also have our radiative heat transfer between them. I define those as intermediates just because I'm going to use them twice in my equations. Okay, so here's my first energy balance. It maps exactly to what you see right over here. I just moved the M CCP onto the right hand side, although that's not necessary. You can write it on the left or right hand side. I'm going to do the same thing for T2, and here you can see that I have Q, C1, 2, and on this side it's positive, and on this side it's negative. So it's just transferring it, the heat back and forth between those two, and that models some of the multivariate effect between them. So we'll have simulation mode, and I'm also going to load in some dynamic data. If you generate your own, then you can just load it in yourself for your file name. Otherwise, you can just read it from this address right here, and there's just some sample data that you can use. I'll go ahead and paste it in here just so you can look at it. Okay, so I had the 601 time steps. Alright, then we have a simulation, and then we'll plot the results. So I'll do the first subplot, and I'll put that in terms of minutes. And then we'll do our second subplot as well, and do our Q values, and then show. Okay, so let's go ahead and run this one just while we're waiting for it to finish, and then we'll get into the deep learning algorithms with GEKKO as well. So here's our energy balance, and I'll run it. And so it's going to need an internet connection if you're going to be accessing these data files. If you run it remotely, then you won't need an internet connection. Okay, so it's going to run, okay, and then bring up our solution. So you can see the measured values, or the thicker line right here, those are the dots. Okay, and then the simulation is the solid line. So there's still a little bit of a mismatch between the two. But it's fairly close, and you could probably adjust the parameters to get it even closer. That's going to be a subject of a future lab assignment, is where we adjust those with optimization to minimize something like a sum of squared errors. Okay, let's go on to the second one. Now this is more of a deep learning approach to doing this model. Let's say we don't know the energy balance, or we just want to use the data to see what it gives us. We can use, a neural network approach, where we're going to be using neurons, these nodes. Each of these circles are neurons, and there are weights that connect those. And if you wanted just a visual overview of neural networks, I would recommend playground.tensorflow.org. In this case, we're going to do 3 layers, and each of them will have 2 neurons. And we're going to be solving a regression case. We're going to try to correlate the heater inputs to steady state temperatures, and then we'll use those steady state temperatures to then correlate to the dynamic temperatures. And we'll use hyperbolic tangent for one of our layers, and then we'll solve this. There you can see the loss function. That's the objective function, and this is like the number of iterations. Epochs are the number of times the weights change. So there you can see the individual neurons and the weights between those. So every line represents an additional output from that neuron that goes then into this next neuron, and then there's a hyperbolic tangent that then translates it into another signal, and there's some additional weights there that are visualized. Okay, so anyway, this is an example, just a visualization of what we're going to be doing. I'll just leave this over to the side here so that we can see it as we're building our neural network model. Okay, so we're going to need a couple packages here. We can either use Keras TensorFlow, which is another popular one, or we can use GEKKO for this. I'm also going to use sklearn, just some pre-processing to do our scaling, and then GEKKO, and then import time. So first step is I'm just going to import some data. I ran this previously, collected the data. It took about 6 hours to collect all the data that I needed. I took steady state data points every 3 minutes, and there are about 120 of them. So that took about 6 hours to collect. Now if you'd like to generate this data set yourself, I am going to put those here in the code. Okay, if you just scroll down here, you can have it generate that file for you if you'd like. So I just included this one, this part of it in this script, but you're welcome to get this one and generate the file yourself with your own device. Okay, so let me come back here. I'm going to scale the data as a first step. Okay, and the neural networks are going to work better if the values are between 0 and 1. And so I'm just going to fit transform with this min-max scaler. Then I'll partition into inputs and outputs. I'll take my scaled X data, my inputs, and take the first 2, which are going to be the heaters, and the second 2, which are going to be the temperatures. And then I'll build the neural network. First of all, I'll have the number of inputs, the hidden layer, which is going to be a linear hidden layer, and then I'll have a nonlinear hyperbolic tangent layer, and then finally another hidden layer. And then I'll have 2 outputs. So most neural networks are, they have 1 output, and you just have different networks to do the different outputs. This one is going to have 2. Okay, and there's my data that it just created, just popped up. We'll use that one later. Okay, then we'll train the GEKKO model. We'll create a training model and then a dynamic prediction. We'll have the 2 different models, And we'll have for M and model, and we'll cycle through this twice just to be able to create both models. I'll use the APOP solver for both of them. I'll have my inputs. These are going to be 2 inputs. N is 2. So I'll just do a list comprehension to define 2 parameters. First layer is going to be the 3-dimensional matrix. I'm going to have number of outputs, which is going to be 2, number of inputs, which is going to be 2, and N1, which are going to be 2 neurons as well. So it's going to be a 2 by 2 by 2 matrix. And then I'll have L1. I'll define those as intermediates. And I just need to have these different list comprehensions to be able to construct all of the different outputs of that first layer. And then I have layer 2, which is going to be hyperbolic tangent. And this one is going to be very similar, but instead of just a linear correlation like I had right here, I'm going to have a hyperbolic tangent and multiply it by the input from the prior layer, the L1. And then I'll have the weight 2 there. Okay, now let's go on to layer 3, which is going to be another linear layer. And here I have another intermediate, and then I have these for J, I, and K. Okay, so moving on, we're going to go to the next one, which is the outputs, and then we'll have 2 outputs. We'll have some equations that are just going to sum up the neurons that are the outputs of the neurons that are in that finer linear layer. And then we'll flatten the matrices. So we have these 3-dimensional matrices, so instead of looping through in a triply nested loop, we're going to just flatten them so we can work with all of the values individually. Next we'll fit some parameter weights. Okay, so we'll have our training model, and then we'll loop through just the 2 inputs, and we'll feed those in. These came from the min-max scalar that we had before, so those are scaled to be between 0 and 1. And then we'll have our outputs as well. These are also scaled between 0 and 1. So these are our heater values, and these are going to be our steady state temperatures that are scaled between 0 and 1. And we'll turn on a feedback status. That means we're going to use the measurement to build our objective function. And then for each of our parameter weights, we're going to turn on the feedback status just so we can insert a new measurement. And we'll turn on the status to tell it that the solver is going to use it to try to minimize the objective function or the loss function. Okay, we're going to do the same thing for W2 and for W3 as well. Then we're going to go on to I mode 2. That's going to be an option that's going to allow us to do the steady state regression. Okay, and then EV type 2, which just means sum of squared errors. Then we're going to solve it, and we'll display the solver output. And then the next step, after we've trained our neural network, we're going to generate some dynamic predictions. So we're going to switch back over to the dynamic model. That's also our neural net model, but then we're going to add a couple things to it. Okay, we're going to define our time. This is our GEKKO time, where we're going to simulate over from 0 to 600 seconds with 601 time points. We'll load the neural network parameters. So this is from our training model. The new value that we got, we're going to load that into the measured value for our dynamic prediction. Okay, so that's our training model right there. Okay, we're going to turn on the feedback status, tell it to use that measurement. We'll do the same thing for W2 and for W3 as well. And then we'll do some step tests. Okay, these are the values that we had defined before. These just step up and down our heater values. We'll do that in simulation, and we'll do it for Q2 as well. Okay, our scaled inputs. Now we've got to get our heater values that we just defined right up there into the 0 to 1 scaling, and so we'll use our scaling values and our shifting values, the minimum, to shift it so it scales it between 0 and 1. And then we'll define the temperature output. Okay, there's our ambient temperature and our initial heater value, and we'll scale the steady state output. Okay, and then we go on to the equations. Okay, these are going to be unscaling the outputs from our neural network, and then subtracting the min, and then dividing by the scale to get it back into degrees Celsius. Okay, then we have our dynamic predictions. This is going to be our taking our steady state temperatures and converting them into dynamic temperatures. And so we'll have a time constant. Just use 120 there for now. We're going to determine that later when we do things like recurrent neural networks to do time series data or other approaches to obtain those parameters. Okay, we have some initial equations here. These are going to be the tau times the derivative of temperature equals minus temperature. You got to subtract the initial condition there, plus the T1 steady state minus the initial temperature as well. Okay, so those are our two equations that convert our steady state values into the dynamic values. Then we'll solve the dynamic simulation, and let's go and import the data that I had generated. In that script that I showed you, you'll also be able to generate your own if you have a device. And then we'll have the plots just to be able to compare the two. Okay, so there it is. There's our neural network. Now if you want to use your own, and we just generated our own, I'll just say file name equals, and then I think I had called it in that other script something like the same thing but .csv. So you can use the file name instead of the URL if you have a file name there. Okay, so let's go ahead and use the file because we just generated it. And let's go back here and go ahead and run it. Okay, so I have this, and I had this file right here that we just generated. And this should have all of our temperature values. Looks like it's locked for editing, probably by Python or something like that. I'll just edit it with Notepad++. Okay, so there it is right there. Okay, let's go ahead and run it now. Go ahead and run this, and it will train the neural network, and then it'll show us our predictions on how well we're predicting with our neural network and the simple dynamic equations that we had there as well. Okay, so let's see. I'm going to let's see. As we create these GEKKO models, you can do remote equals false. If you want to just use your local computer, let's say your internet connection's slow or something like that, you can always go to remote equals false, and it won't use those. I guess it is trying to go out and get this data file as well. So let me try it just one more time and see if it'll go out and request that. Okay, so it got the file and then is running it, and there you can see the data that we just generated versus the model predictions. And so this solid line is what is predicting what would have happened with these heater values. Now you can see it's off by just a little bit, but it's actually doing quite a good job here. So fairly close just with the neural network model that we had. Okay, so that concludes this video. Okay, we've gone through just a lot of things. We went very, very fast through this. So let me give just an overview again of what we just covered. We we have this data right here, and we wanted to try to predict by using an energy balance, first principles approach, but then also use a neural network, a deep learning approach, where we had these hidden layers, and we tried to use this machine learning approach to obtain them. So it just compares and contrasts this, the two different approaches, either using fundamentals, first principles, versus a deep learning method. So both have their merits. I'd say that if you have fundamental knowledge, then you try to insert that into your application. But if not, if you have a lot of data, that's very good data, then you might be able to do just as good a job with deep learning approach. Now we're going to go through our next ones. We're going to be doing, if you come back to the Arduino lab page, our next labs are listed here, where we're going to take this data and then do some additional parameter estimation, empirical model estimation, and also combining the deep learning and the first principles approach into one with the hybrid model estimation. And then we'll get on to control with linear model predictive control, nonlinear model predictive control, and then using an estimator with our MPC.